This is a coded illustration of an attack against RSA encryption in which we'll be playing the role of a third-party interceptor interested in computing the value of the decryption key D using the publicly available values of N and E and no private information. So I talk quite a bit on this channel about how one could go about finding secret information from only public information in RSA cryptography. If you're familiar with some of my earlier content, you'll recall that I talk about two main decryption techniques that are available to interceptors who want to access private information, which include values of P, Q, phi n, and D, using only the publicly available information that they have at their disposal. That is, values of N and E. The first one of those techniques is large semi-prime factorization. One could take that publicly available value of N, seen here, factor it into its factors P and Q, find the value of phi n by plugging in P and Q into the equation phi n is equal to P minus 1 times Q minus 1, and then plug in phi n as well as that other bit of publicly available information E into the equation E times D mod phi n is equal to 1, and then solve for D. With that value of D, an interceptor could unlock any encrypted message that used this particular scheme that came their way. Factoring is easy enough to do for really small values of N, but when N is hundreds of digits long, as it typically is in real life, finding its factors P and Q becomes incredibly time-consuming, so an interceptor couldn't feasibly use this technique in real life to do any damage to information protected with RSA. The second decryption technique involves calculating D directly. An interceptor could theoretically generate some integer message M, use the publicly available values of N and E to encrypt it by raising M to the E power, dividing by N, and taking the modulus of that division to yield a ciphertext message C. The interceptor could then take that ciphertext message C, raise it to the still unknown D power, plug in the value of N, and know that the result of this expression would be equivalent to the original integer secret message that they first generated. They then would have one equation where the only unknown value is D. So what I'd like to do today is take a look at what a program that tries to calculate D in this way might look like. I'm going to be using C++ and Xcode to demonstrate this today. So the first thing that I'm going to do is go ahead and write in some include statements for CMath and numeric. CMath and numeric. I'm also going to be including something called the Boost Multi-Precision library today, which lets me deal with really big integers beyond what C++'s ordinary capacity for dealing with such numbers might be. So I'm going to write include boost slash multi-precision slash cpp underscore int dot hpp. Not familiar with Boost, or you don't know how to link it to your Xcode project, I made a video explaining how to use it in your Xcode programs, and I'll go ahead and put the link for that in the description down below. And so I'm also going to write that I'm using the namespace std, and I'm also going to be using boost multi-precision cpp underscore int. And so now I'm going to create a class called direct attack. So I'm going to say down here class direct attack. And I'm also going to create some public variables and functions along with that. Firstly, I'm going to create two unsigned variables. My first one is going to be denoted n, and my second will be denoted e. And these are both going to act as bits of public information that are available to everybody in a typical RSA encryption scheme. So I'll just write public information, public information. I'm also going to create two boost variables, m and e. So I'm going to write boost multi-precision cpp underscore int m. And I'll just go ahead and copy this. For C. So M is, of course, that secret message that we, as the interceptors, are going to generate, and C is the ciphertext message, which is just going to represent our secret message in its encrypted format. I am next going to create a prompter function. And the prompter function is going to have the job that it will ask for those two public bits of information, n and e. And I'm also going to create a boost function called encrypt, whose function it will be to encrypt our secret message m. And finally, I'm going to create another boost function, which I'm going to call calculate d, and this will accomplish the main function of this project, which is to calculate d in a direct manner from only public information. So now I'm going to move on to defining these functions that I just declared. I'm going to start with my prompter function, so I'll write void direct attack, prompter. Now I'll simply see out a statement that asks for the publicly available values of n, for the publicly available value of n and c at n. So I'll see out, please enter in publicly available n. And I'll go ahead and see it in, and then I'll copy this and replace n with e. And this is all that I want my prompter function to do, so I'm now going to move on to writing the implementation for my encrypt function. Since this is a boost function, I'll write boost multi-precision cpp int direct attack encrypt. Now, keeping in mind that raising a secret message m to the e power mod n will give me a ciphertext message c, I will see out a statement that asks for a secret message m input and see in the value that I get from that. So I'll write see out, please enter in a message m to encrypt. And I will see in that value of m. So now I can write that c is equal to pow m e mod n. that is m to the e power mod n. Now, since I am going to be dealing with pretty large numbers given this degree of exponentiation, I need to specify boost multiprecision several times in this statement. Firstly with m, then with the pow function itself, and finally with the result of that entire exponentiation. And so this function is something that I go a bit more into detail in my previous video. So again, check that out if you'd like to hear more about this specific function more in depth. And so after this, I can simply return C. Now I can move on to the most important function in this program, and that is the calculate D function. So now, keeping in mind that c to the d power mod n is supposed to yield my original integer message m, at this point we, as the interceptors, have the value of m right here because we generated it, and we also have a corresponding value of c here, which is simply m in its encrypted form. And we also have n here, since that's publicly available. So all that remains to do is to write a program which will compute d for us, the remaining unknown. The first and most obvious way of computing d is to simply start at d equals 1 and keep incrementing d until both sides of our equation match. The first thing that I'll do then is create an unsigned variable d and set it equal to 1. From there, I can create a while loop and say that while pow c d, so that is c to the d power, so while pow c d mod n does not equal 1. Does not equal m, then increment d by 1. And again, since I'm dealing with such a level of exponentiation, I'm going to add in some boosts, just like I did with my previous encrypt function. So I'll add in a boost in front of c, in front of pow, and in front of this. And a few extra parentheses. And after this, I can simply return d. Now, this is not the only way that I can calculate d, so I'm going to temporarily comment this stuff out so that I can show you the other way. So going back up to my equation here, let's say that I have 106 to the d power mod 143 is equal to 24, and I want to find d. What I just coded is basically just plugging in values of d until both sides of the equation match. But I can also reason that, okay, 106 to the d might be 24 more than 143, so that is 143 plus 24 mod 143 is equal to 24, and this is of course a true statement. So what I can then do is set 106 to the d power equal to 143 plus 24, which means that 106 to the d is equal to 167. And so then I can take the log of both sides of the equation. So log of 106 to the d power is equal to log of 167. And so then I know that d times the log of 106 is equal to the log of 167. And I can conclude that d is equal to log of 167 divided by log of 106. When I do this, though, in this particular case, log of 167 divided by log of 106 happens to take on a decimal value, which d, of course, can't be. However, I can fix this by keeping on multiplying the value of 143 by a steadily increasing constant. So I can say that 106 to the d is equal to 143 times 2, say, plus 24, and then solve for d. Or I can say that 106 to the d power is equal to 143 times 3 plus 24, or times 4 plus 24, and then solve. And I can just keep on increasing that constant value until I get a non-decimal value of d. So now I'm going to try to write some code that executes that incrementation process for me. First, I'm going to create an unsigned variable that I'm going to call counter and set it equal to 1. And this is going to act as that increasing constant that I just talked about. Then I'm going to make a while loop that involves fmod. And I'm going to use fmod this time around instead of just plain modulus, because fmod is equipped to deal with variables of the type double. And since I'm going to be working with logs, which are doubles in C++, I'm also going to be working with fmod. So after this comma in fmod, I'm going to put 1, and after this does not equal 0, because I want to check that what goes before this comma here, I divide by 1 and take the modulus of that division. I want to ensure that I'm only getting a result that equals 0. So that is, I want the result to be non-decimal. So to figure out what I need to put here, I'm going to look back up here to what d equals and find that in this particular case, 167 is equal to 143 times 1 as the value of my counter in this particular case, plus 24. 143 is, of course, my value of n. 1 is the value of my counter. 24 is the value of the secret message m. And 106 is the value of that ciphertext message. I also want to static cast n counter, n times counter plus m as a double. And I want to do the same thing with C. And so I'm going to take this entire thing, throw some parentheses around it, and copy it down here. So then I can say that while that entire thing does not equal 0, then increment the counter. After that, I can simply copy this statement from up here, paste it down here, and then return D. And I'll specify D as unsigned. since I haven't defined it yet. And so the way that we're going to eventually end up computing D using this method is by incrementing that counter. I'm going to test out both of these methods in just a moment, starting with the first one that we coded. So I'm going to uncomment it out and comment out what we just coded here. And now I can go into int main and create a try block. I'm going to first create an object of the class direct attack, which I'm going to call object1. Then I'm going to say object1.prompter to test my prompter function, and I'm going to cout object1.encrypt to test the encrypt function. I'm also going to cout object1.calculate d to test out the calculate d function. Then I can catch runtime error and cout s.what and then return 0. So I can then go ahead and run my program. And I'm prompted for a publicly available value of n, so I'll give it a known semi-prime number, 3233, and a known value of e, say 7, and I'll give it the integer message 89 to encrypt. So then I get an encrypted value of 206, so that's my value of c, and I get a value of d that's computed as 223. So let's verify that this value of d is a legitimate one by testing it with Wolfram Alpha. So I'm going to say that 206, which is my encrypted value, raise it to the 223 power, and say mod the value of n, which is 3233. And it looks like I'm getting an output of 89, which was my original secret message that I inputted back here. So it looks like this value of d is a legitimate one. And this decryption method appears to be working. So now I want to test out my second method. So I'm going to comment this out, this first method, and uncomment this, and then run my program again. So I'll give it again 3233 as my value of n, 7 as a value of e, and 89 to encrypt. And it looks like my program is really struggling to compute a value of d in this way. Yeah, and sure enough, it looks like my program was not able to compute d using this second method. So let's check back with Wolfram Alpha to figure out why this is happening. So from my first run of the program, I know that 223 is a valid value of d. So I can say that 223 is equal to log of 3233 times that counter, which I'm going to call x here, plus the secret message 89, divided by log of the ciphertext message 206. It looks like that the value of that counter x is absolutely astronomical, so no wonder why my program was unable to compute a value of d using our second technique. So it looks like In this particular instance, at least, it's actually a lot more time efficient to just keep on incrementing d until both sides of my equation match. It's important to note that although my program was able to calculate d using the first technique that we tried, in the real world it would likely not be feasible to simply keep incrementing d due to the sheer massiveness of numbers typically utilized in real-world RSA encryption. But nonetheless, I think it's interesting to see what a potential attack on RSA might look like, even if it is on this small scale. Well, I hope this was interesting and helpful. Thank you so much for listening, and as always, stay safe out there.